All right, since it's been almost a week since we've covered E2 reactions, I figured we should start with a brief summary of what we covered last week. And so let's make some brief review that I want you guys to help me out with. I'm going to pick a generic substrate and I'm going to pick a generic base. What product or products should we get out of this reaction? What do you guys think? How many beta protons do we have? Well, we've got beta protons here and here. So if we grab one of those, we'll get a trans product. If we grab the other one, we'll get a cis product. And is that it?
No.
Nope, we've got beta protons over here. And if we grab one of these beta protons, that means that we will end up with this alkene. What do we call these two products? It was named after a chemist. Zaitsev. And then this one was our Hofmann product. All right, so let's talk a little bit about this. What sort of base do we need for an E2 reaction? Yeah, E2 reactions require strong bases. A weak base will not work. So what are some examples? What are some examples of really strong bases that we can use for an E2 reaction? Okay, I heard a bunch of them. So let's do NaOH. What's another one? So sodium hydride. That's great. Anybody have some others? Don't be shy. What was the funny acronym sounding one? It was a bicyclic ring. Does anybody remember those? What was that? Close. It starts with a D. There was DBU. And then DBN. And then we also talked about how we could use things like sodium ethoxide, or we could use sodium terbutoxide, etc. There's a lot of them we could use. In this case, they fall into two general classes. What's different between sodium hydride and sodium hydroxide? Yeah, the oxygen. What else? Sodium hydroxide, we saw hydroxide can do substitution reactions. Can sodium hydride do a substitution reaction? No. So in this case, they fall into two classes. The first class are non-nucleophilic. And then the bottom class can be nucleophiles. And so we do run into a problem where if we are trying to do an E2 reaction and we choose a base that is also a nucleophile, we have to be aware that there might be a substitution product. All right, what about favoring Zaitsev products? What sort of bases would favor Zaitsev? Small. Okay, so small bases, meaning they're unhindered, favor Zaitsev. Conversely, large hindered bases favor the Hofmann product. Why don't we get the more substituted alkene if we're using a really big base? Yeah, the base has a hard time approaching those protons, so with a large base, you're always going to get your less substituted alkene as your major product. And then on the exam, I said that elimination is favored at high temperature. That's true for both E1 and E2, and we're going to talk more about E1 today. And then the thing I was really trying to drill into you guys was that the beta proton must be anticoplanar to the leaving group for an E2 reaction. Does the beta proton orientation matter for an E1 reaction? No, because we're going through something that's planar. But with an E2, we have to make sure that that beta proton's anticoplanar. And in this case, the substrate can be primary, secondary, or tertiary for an E2 reaction. Why can't we do E2 off of a methyl carbon? What do you guys think? Let's think about a methyl carbon where we've got our 3 hydrogens and we've got our leaving group and we've got our base. Why won't this do elimination?
Because there's no other carbon forming alkene.
Exactly. There are no beta protons specifically, and there's no way to form an alkene with the methyl group. But with E2 reactions, unlike SN2, it will work on a tertiary substrate because all it needs is beta protons. It's not trying to do a nucleophilic attack. It just needs to pluck off a proton. Important thing to remember is if you see a methyl group, it immediately eliminates the possibility of an E2 reaction. So no E2 with methyl carbons.
That applies to E1 as well, I assume.
Yes, that applies to E1 as well. So let's even add that in. No E2 or E1 with methyl carbons. All right, so now let's go into a little bit of detail on the E1 mechanism. The E1 mechanism is a lot easier than E2, so we'll be able to cover this fairly quickly. And the E1 mechanism that we had in class, we said the first step involves what? Yeah, the leaving group falls off. So we have to be able to form a stable carbocation. And then we said that we only need a weak base that can come and grab our beta proton, clamp down, and form our alkene. And there we go. So let me add in our leaving groups too. Just to be thorough. All right, what do we know about the leaving group for these reactions, for E1 or SN1? Yeah, we must have a good leaving group. So must have a good leaving group. Second thing was we must be able to form a relatively stable carbocation. Will we observe this with a primary carbon? No, not unless there's a rearrangement opportunity available. So in this case, it must be able to form a relatively stable carbocation or rearrange into one. In this case, it won't work really ever with the primary carbon. Third thing is we only need a weak base to deprotonate the beta proton. Why do we only need a weak base in this case instead of a strong base? What was that? Yeah, it doesn't have to compete with the leaving group. And if we think about our carbocation, it's so high in energy, it'll react with practically anything. It just needs a slight nudge in order for that proton to be deprotonated. What if we use a really strong base? Would it be an E1 reaction anymore? What would happen if we had a strong base? It would do E2. So even though it's a tertiary carbon, it could still do an E2 reaction. So we only want a weak base. So let's make a note of that. Strong base will give E2, not E1. Second thing is that your beta proton is always next to your carbocation. Even if it rearranges, as we saw in our previous problem of the day, the beta proton could change locations. It's always going to be the proton that's adjacent to that carbocation carbon. And we said that it doesn't, the beta proton doesn't need to be anticoplanar. Which makes these reactions a lot easier to anticipate. The other nice thing with a E1 reaction is that the reaction always favors your Zaitsev product. Your Hofmann product will be minor. And again, this has to do with the instability of the carbocation. It's so reactive that it will immediately want to react and form your most stable product. The one bad thing with an SN or an E1 reaction is that you're always in competition with an SN1 reaction for the most part. So it often results in SN1 E1 mix. What's one way we could favor the E1 elimination over the SN1 elimination? Heat it up. So if you are a chemist and you want to favor the E1 elimination, you heat it up. If you want to favor the SN1 reaction, you can cool it down.
So you said we don't really talk about the Hofmann test in the E1 reaction, but you still label it in the summary for...
Yeah, in this case, we still call it a Zaitsev product, but we don't have a way of controlling it so that we get the major product as a Hofmann product. It will always favor your most thermodynamic product. So with an E1, always remember it's going to favor the more substituted alkene, not your less substituted alkene.
So it's kind of like 99% of the Zaitsev and 1% of the Hofmann?
It really depends on the situation. There are a bunch of variables you'd have to take into account, but your major product will always be your Zaitsev.
So what do you mean when we talk about the E1 reaction, we does not really talk about the Zaitsev and the Hofmann?
You can still label them. Most people will just say the more substituted product will always be your major product. When you're hearing Zaitsev and Hofmann, it's usually in relation to an E2 reaction, although it can be applied to E1 as well.
Okay.
Yep. All right, so let's take a look at some examples for these reactions. And this might give you a little bit of practice for the cyclohexene lab report if you haven't worked on it already. Let's do tonight. All right, so this first reaction, we've got catalytic acid. So I often draw a catalytic acid as H plus in brackets and then write cat underneath it. What will happen here? Yeah, we're going to protonate it first. Fastest reaction in chemistry is always protonation. Now we've got water. Water is a good leaving group. What's going to happen next? Water is going to leave. Oop. All right, now what?
There's going to be a shift.
Yeah, we could do a 1,2 methyl shift. So that's one option. So I'm going to draw this out here. All right, and we've got water floating around. What could happen next?
Wait, you positive charge.
Oops, sorry, I put it on the wrong carbon. Thank you. All right, what will happen next? Deprotonation, doesn't matter which beta proton we select. Well, if we think about our beta protons, we've got one beta proton here. We've got 3 of them out here.
There's one more.
And we've got 2 of them over here. So we've got a bunch of different beta protons we could choose. So we have to anticipate all 3 of these different products. So if we do the one on the far left, we would get a double bond here. If we did the one on the top, we'd get a double bond here. And if we did the other one, we would get a double bond here. Which one's going to be our major product?
It's the top one.
The top one. Why the top one?
Most substitute.
Most substituted. Also, with an E1 reaction, oftentimes you will observe other products that occur prior to deprotonation, or prior to rearrangement, I should say. So if we look at this, there are beta protons right here and here, which if we had water could deprotonate one of those and give you this product as well. So one big problem with an E1 reaction or an SN1 reaction is you occasionally get this horrendous mixture of products out of it. Your major product is always going to be your most substituted alkene, but you might observe trace amounts of any of these other 3 minor products that we have shown. So it can be a little tricky. All right, let's try one more. And this time I want you guys to work with a partner or on your own, and I'll give you guys a few minutes to work on this.
After you write that up, you can go back.
Yeah. All right, so again, we've got acid, we've got a catalytic amount of acid and heat. And do you want me to scroll up further than this? More? All right, I'll wait for everybody to copy down the example problem, and then I'll scroll back up again. Does everybody have the example problem written down?
Yes.
Okay, so I'll scroll up for Ramon so you can see everything.
Thank you.
Mind if I scroll up? Okay. So let's get started. I'll at least get us started with the protonation step. That one's nice and easy. Second step, we said for E1 is always our leaving group falling off. Now what? Okay. So am I going to move hydride from here? Nope. Because that would again give us a secondary carbon. So what we're going to do is move this hydride over to this carbocation. That'll move our positive charge here. And then we have to ask ourselves, all right, what product or products could we get out of this?
Wait, where did the hydrogen shift?
What's that?
Where did the hydrogen shift?
So why did we do a hydride shift instead of a methyl shift?
Yeah.
Because if we did a methyl shift, again, we'd be stuck at a secondary carbocation. The hydride shift is what allows the carbocation to go from secondary to tertiary.
So you mean we move the methyl, then we form another secondary compound, so it's meaningless.
Yeah, so you only do rearrangements if you're going to a more stable carbocation. You won't go to an equally stable or even less stable carbocation.
Okay.
All right, so let's look at potential products for this. All right, let's say we grab beta protons from the top there, or we grab beta protons from the bottom, right? So if we look at this, we could say there's beta protons on this carbon, which could give the alkene in that top position, or there's beta protons right here. Do we agree that these are two different products? Ah.
It's not.
What's going on here?
Because it can twist.
These are the same products, right? This is a sigma bond that can spin around and be the same product. So we don't need to draw the same product twice. So I'm going to erase this and say, all right, that's product one. Are there any other products? Yeah, exactly. So if we look at this, we could say, all right, we've got beta protons here and here, which means we're going to also have this product. Which one's going to be our major product, the left or the right? The left. So we could say, all right, this one's going to be our major product. And then if we think about this, this could also have many other minor products. Because if we look at this, there are beta protons in either position, and then we could also get mixtures of cis and trans as well. Yep.
Why can't you get like a mixture of, it's not cis or trans, but like cis or trans for that major product? Like why can't like it
For this one?
on it? Yeah.
So if we move the ethyl group to the other side, it'd be the exact same product. Right? Because we've got two methyl groups here, we've got symmetry, and it doesn't matter which side that ethyl group's on. It's a good question. So oftentimes with E1 reactions on exams and quizzes, if I am asking you for a product, I'll try to specify the major product, because quite frequently with an E1 reaction, you get a mixture of like 5, 6, 7, or even more different products out of that.
So over there, why did we do a hydride shift instead of just making a double bond? Is it because that's not a beta proton?
So usually the major product is going to be the result of a rearrangement reaction if it can form a more stable carbocation. But you're right. With that secondary carbocation, we do have beta protons, and we could do an E1 elimination off of that, but it's going to be a very minor product. Yeah. All right, one thing to note, too, with these E1 reactions is you notice how in each case I used acid and heat. Acid and heat on a secondary carbon is a big giveaway that it's an E1 reaction. So let's write that down as a trick. So trick. Catalytic acid plus heat equals an E1. This is one of the few cases where you don't really observe the SN1 reaction happening because it would just give you the same product back out. But it will give you the E1 product out of this.
What is the catalytic acid?
So just like in lab when we worked with cyclohexanol, we didn't add a full stoichiometric amount of acid. We added just a milliliter or two, and that was enough to drive the reaction because the acid gets recycled through the whole reaction. So you don't have to worry about it getting all used up. All right, so now the tricky part for this chapter. We're not going to spend very much time on E1 because it's fairly intuitive.